Welcome to the 6.4 notes. We're going to be looking at graphs of polar curves and looking for patterns with different equations and what do they mean and why do we get the types of pictures that we get and how could we graph them with a calculator and even on our own. So really today is a lot of exploration and looking at patterns. To start off with, you can use a scientific calculator on this portion. And let's consider the polar equation r is equal to 3 sine of theta. And what we're going to do is we're going to substitute in various different values for theta. We're going to be in radians and sketch a polar curve. So set your calculator into radians and you could plug them in. I mean, we know that the sine of 0 is 0. So 3 times 0 is 0. If you plug in pi over 6, the sine of pi over 6 is 1/2. You could just type 3 sine pi over 6 in your calculator, but 3 times 1/2 is 1.5, and so forth. And we could do that for each of these angle measurements. Let's see what we get. Sorry, my computer is making a lot of noise at me. All right, well, let's plot these. So right here, if I go 0 units out in the direction of 0, I'm actually at the origin. And if I move out 1.5 units in the direction of pi over 6, here's where pi over 6 is. 1.5 units would be here. Like that. And then if I move out 2.1 units in the direction of pi over 4 is like right here. And if I move out just a little bit more than 2.1, I'm going to estimate where that is. And then if I move out 2.6 units in the direction of pi over 3, here's pi over 3. So 2.3. And then if I move out 3 units in the direction of pi over 2, and then 2.6 units in the direction of pi over 3. I don't think that was actually 2.6. I think 2.6 would be more like 2.5. Sorry. 2.6 units in the direction of 2 pi over 3. 2.1 units in the direction of 3 pi over 4, which is like here. And 1.5 units in the direction of 5 pi over 6. And then back down to 0 for pi. And if I kind of connect these, I'm going to get this circle, this really badly drawn circle. So 3 sine theta is a circle. If I look at this circle, maybe if I draw it a little bit better, this circle has a diameter of 3. A diameter of 3. Not a radius of 3, but a diameter of 3, and it's along the y-axis. It's symmetrical to the positive y-axis. Let's do this one, 3 cosine of theta. Very similar. You're just going to, you can use your calculator to plug these in. 3 times the cosine of 0 is, cosine of 0 is 1. So that's 3. 3 times the cosine of pi over 6, and I'm just going to round this around 2.6, 2.1, 1.5. You're seeing the similar values as we did before, but not quite the same. You might remember that sine and cosine, when we do complementary angles with sine and cosine, we get the same values. But cosine at times will have some negative values. Sine at times will have negative values, depending what quadrant we're looking at. So these ones have some negatives, because anytime we're in quadrant 2 with our angle measurements, we can get some negative values. I think this is actually -3 right there. My apologies. All right, well, let's plot these. So if we're looking at the 0 radians angle right here, we're going to go 3 units out for the radius. In the direction of pi over 6, we will go 2.6 units, so a little bit more than 2.5. Pi over 4 is right here. I'm going to, in that direction, in that position, go out 2.1 units. At pi over 2, I will go out no units, so I'll go back down to 0. And now in the direction of 2 pi over 3, I'm going to go -1.5 units. Well, 2 pi over 3 is here, so I'm going to go backwards -1.5 units. And, I think I forgot to graph my pi over 3 at 1.5. Let's try that again. I skipped that one. And then in the direction of 3 pi over 4, which is right here, like this angle, I'm going to go back -2.1. in the direction of 5 pi over 6, I'm going to go backwards, negative 2.6, 1, 2.5, a little bit more than 2.5. And then at pi, I'll go back negative 3, which actually lands on a point I already have. Well, if you connect the dots here, we have another circle. But notice the difference between 3 sine of theta and 3 cosine of theta. They're both circles. They're both circles with a diameter of 3, not a radius of 3, but a diameter of 3. But their positioning is different. Sine is positioned along the positive y-axis versus cosine is positioned along the positive x-axis. Hopefully that relates to you. Cosine is usually x, sine is y, so that would make some sense. We're going to do a little bit more exploration. We're going to go to this exploration. It's from a company called Mathematic. It's slightly modified, but we're going to be going to, this link will take you to Desmos, so this link will be sent to you in Canvas. And the folder for part 1 should be open, and what we're going to be looking at is the graph of r equals a cosine of theta, and see what happens if we change what value a is. So what we can do is we can press play on the button for slider a, or we can manually change the slider. It'll change what values we're using for a. We want to observe how the graph changes, and this should reinforce what we just saw at the Explore earlier. And then we're going to turn off that graph, and we're going to open up the graph for r equals, I think there's a typo here, a sine of theta. And again, we're going to use the slider to kind of see what's happening there and explore. After we're done with that, we're going to turn off that graph and close the folder for part 1. We'll be exploring part 2's folder on the next page. And we want to be able to fill out this and figure out what's happening in this equation. In these forms, these polar equations, these curves, what do they end up looking like? And then we're going to do a little graphing in this table. All right, so here is the Desmos exploration right here. Let me see if I can kind of get this a little bit better in our image on our video screen. Let me see if I can get this to fit. Okay, so what I've got is I've got the graph of r equals a cosine of theta on. By the way, if I wanted to look at r sine theta, it would be that one, which is green. The colors indicate. I can click it again and turn it off. What I'm going to do is right now a is 3, which is actually the same one that we just explored. I'm going to change what a is. As a gets larger, notice how my diameter of the circle gets larger, but it's still along the x-axis. Gets smaller, that diameter decreases. But what if I start using some really small values, like 0? Notice how that's just a point. But what if I use a negative? Still a circle. The diameter is the absolute value of a, but now I'm on the left side. I'm still on the x-axis because this is cosine, but I'm on the left side. So you can kind of see what happens here. I'm now going to turn off that graph and turn on this one. This one, a is 4 right now. I'll switch a to be 3. This was the one we explored. If I change what a is, it changes the diameter. I'm on the y-axis since this is sine, the positive y-axis if a is positive. But if a is negative, I'm on the negative side of the y-axis. So following the directions, I'm actually going to go ahead now and turn that graph off so nothing is being graphed. And I'm going to go ahead and close up this folder here. So I'm just going to close that. Oops, I guess I closed the wrong thing. Let me close part 1. So I'm going to shrink that down. And part 2 is what I'm going to be doing on the next page. But let me just go back to the notes. So I'm going to fill this out. What these are all circles. And so if we see r equals a cosine theta, that's a circle. And it's along the x-axis. And a is going to give us the diameter of the circle. R equals, I sound like a pirate, R equals a sine of theta will be another circle, but this would be along the y-axis. It's like symmetrical along these axes. And if a is positive, we are on the positive side of the x-axis. So diameter's 2. I'll just do it at my best effort. Evidently, that's my best effort to draw a circle there with a diameter of 2. If r is negative 2, that would be a circle on the negative side of the x-axis with a diameter of 2. R equals 2 sine of theta would be a circle along the positive side of the y-axis. R equals negative 2 sine of theta would be a circle along the negative side of the y-axis. Now, if worst comes to worst, you could always make a table of values to do these, which we'll provide a table in case you ever want to use it. So that's how circles look. As long as these circles are kind of, if it's centered at the origin, this is back from last class, like y equals 3 would be going out 3 units in each direction. So that's slightly different. That one, the radius is 3 rather than the diameter. And that's centered at the origin. These other ones are not centered at the origin. They touch the origin, they touch the pole, but they go out from there, whatever length A is for the diameter. All right, let's go to the next page. We're now going to open folder 2. We're going to look at graphs r equals a cosine of n theta. So we're going to have this number that multiplies theta for both cosine and sine, and they're called Rose curves. We're going to start with equation 6, and let's see what happens when we press the A slider. And then we're going to also press the N slider and see what's happening. Okay, so we're in folder 2. I'm going to turn on this one. Interesting. This is not a circle anymore. So this is r equals a cosine of n theta. And this one, A is up here as a slider, and I can change what A is, which we will, and then N is down here. So right now N is 2. This is negative 10 cosine of 2 theta. Well, let's change what A is. So if I change A, it changes. These are called Rose curves. These little pieces are each called petals. This one has 4 petals. A changes the size of the petal. I'm going to go back to the notes. So A changes the size of the petal, or the length of each petal changes when we change what A is. Now I'm going to check N and see what happens if I change N. So that's another slider down here. So right now N is 2. There's 4 petals. Look for a pattern. Now N is 3. And we have 3 petals. Now N is 4. We have 8 petals. N is 5, and I have 5 petals. N is 6. I have 12 petals. 7 petals. 16 petals? Weird. Very odd. Speaking of odd, let's look and see what happens when they're odd petals. 1, N is 1, we have 1 petal. N is 3, we have 3 petals. N is 5, we have 5 petals. N is 7, we have 7 petals. So if N is odd, that tells us the number of petals. If N is even, let's see what happens with even. N is 2, we have 4 petals. Now we have 8 petals, 12 petals, 16 petals. So if N is an even number, the number of petals is twice as many as N. Interesting. Something else I want you to notice, remember this one's a cosine graph. No matter how many petals we have on this, I want you to notice that at least one of them is always going to be centered along the x-axis. Maybe the positive side, but maybe the negative side. Along the x-axis, you're always going to have at least one petal. Even if we had a negative number for N, we will always have at least one petal along the x-axis. Often we'll have 2. All right, so let's see if we can put some of that down on paper. So N changes the number of petals. And what we're going to do now is change both A and N, see what the picture looks like, and then try to replicate it. 5 cosine of 3 theta. So we're going to do 5 for A, make A 5. And then I want N to be 3, N cosine of 3 theta. This is what it looks like. So we have 3 petals. They are going out 5 units. One of them is along the x-axis, and then the other 2 are kind of in those interesting little spots. 1, 2, 3, 4, 5. We're just going to sketch 1, 2, 3, 4, 5, where they kind of look like they go. Now we're going to learn some strategies on how we're going to figure out more about these petals. Let's do this one, negative 4 cosine of 5 theta. So I'll change A to negative 4. My petals are 4 units long. Cosine of 5 theta, I have 5 petals. I have one along the x-axis. This time it's along the negative side. And then kind of, these ones kind of show up. All right, so let's see if I can we're just sketching. Don't get too stressed about this. So -4. So I got a petal there, and then it looks like there was one kind of here, 4 units long. 1, 2, 3, where I think about 4 is. Maybe somewhere around here. I'm trying to remember. I think that one I did 5 by accident. Go back and look at the picture. Looks like something over here. And maybe something over here. It kind of was symmetrical. Maybe it was more like there. All right, 5 cosine of 2 theta. 5 cosine of 2 theta. All right, 4 petals. They're all along the axes, 5 units long each. That one's not as hard to draw. And so I'm just going to do a quick sketch. I think that was only 4. It's super beautiful, my sketches. I'm sorry. Okay. And then 3 cosine of 4 theta. 3 cosine of 4 theta. 3 cosine of 4 theta. All right, so I've got 8 petals. 4 of them are along the axes. They all are length 3, and then these other ones are right smack dab in the middle at like pi over 4 multiples. So lengths of 3 units long along all the axes and then halfway in between. Supposedly length of 3, which I'm doing awesome with. You might be doing better. All right, how can we tell from the equation how many petals there were? Well, if n is an even number, then the number of petals is twice that. But if n's odd, then the number of petals is n. If we look at each of these equations up above, if I plug in the number 0, what do I get? Well, this one, if I plug in a 0, 5 times the cosine of 0 is 5. There it is. Here, if I plug in a 0, I get cosine of 0 is 0 times -4, or is 1. Oh my gosh, 5 times the cosine of 0 is 5, because 5 times 1. Here, 4 times -4 times 1. So in the direction of 0, I go -4 this way. This gives us where this petal is. If I plug in a 0 for this one, 2 times 0 is 0. Cosine of 0 is 1 times 5. Gives me that petal. And here, if I plug in a 0, I get 1. Cosine of 0 is 1 times 3 is 3. So that can give us one of our petals. It might be on the negative side depending on what you get when you plug things in, or if you get this negative out front, but that can give you one of the petals. So there's always one petal at least along the x-axis. Sometimes there's more than one. If there's an even number of petals, you're going to see 2 petals along both of those axes, which is nice. Kind of a nice way to kind of see that. So if there's only one, if it's an odd number of petals, you would not see a symmetry along the other side. How could we know the number? How could knowing the number of petals and the fact that rose curves have that symmetry to find the other ones? Well, we could take our circle like 2 pi and divide it by the number of petals to see how far apart the petals are. And we'll practice that. We'll kind of see what happens with that in a minute. All right, let's turn off the graph of our cosine, turn on our sine. We're going to kind of explore again and then sketch each of these. So I'm going to turn this one off, the purple one off, and turn on this one. So this is sine. We're going to start by exploring. Maybe I'll just put this at something easy. I'll put it at 2. Notice 4 petals because n is even. And if I move around with A, I will see all sorts of size changes. for those petals. And if I change n, it'll change how many petals. But something that we should notice for this one is the symmetry along the y-axis. This is a sine graph. A rose curve with a sine graph will always have this symmetry along the y-axis. Now, it doesn't mean that there's a petal along the y-axis. It means there's symmetry along the y-axis. On both sides of the y-axis, we're going to see symmetry for at least one petal. In fact, if there's an even number of petals, you're not going to see any on the y-axis. If there's an odd number, you'll see one of them. All right, so now what I'm going to do is I'm going to pause this video so that you can go back to the Desmos, change the sliders, and sketch these graphs, and then we'll restart and kind of talk about some patterns here. All right, so I've got some pictures drawn on here, and I'd like you to notice that if there's an odd number of petals, and it's a sine rose curve graph, that we will have a petal along one of the y-axes, either the positive side or the negative side. If it's an even curve, we will not have any along the y-axis, but there'll be symmetry there. And something else I'd like you to notice is there is never a petal right along the x-axis for these sine rose curves. Why is that? Like, why would we never have one there? It's because if we plug in a 0 or a pi, n times 0 would be a 0, and that would always be a 0. Sine of 0 is 0. And if I put in a multiple of pi, whether it was 1 pi or 2 pi or whatever, sine of pi, any multiple of pi times n is going to be 0. N times a is 0. So we wouldn't have a petal there because we would go back to the origin at that point, or back to the pole. All right, so here's what's happening with polar equations of rose curves. They would have this format: a cosine of n theta or a sine of n theta. If n is odd, we have n petals of length n, of length a. And there's some pictures on here for you to look at. If n is even, we'll have 2n petals of length a. A couple hints. Each petal is always length a. They will always be divided symmetrically about the circle. So once you know the number of petals, that can help you make sure your graph looks symmetrical. You can plot a few points that would give you useful values. Cosine, I would always start at 0. Sine, you want to get a pi over 2 as your argument. And there's a multiplier of n, so you kind of have to think about that, but we'll practice this. We're going to practice graphing these ones without using a calculator or Desmos. So some things that we should know here on this one would have 3 petals, because n is an odd number, and each petal will be 7 units long. So something that I sometimes do when I'm graphing these is I'll go out, figure out what circle is 7. 1, 2, 3, 4, 5, 6, 7. Okay, that's this outer. So all my petals are going to go out to that outer edge as I draw this. There's going to be 3 of them. Well, what I want to do is try to figure out what can I plug in for theta so that my argument's a pi over 2. Well, if I start with pi over 6 for theta, and I plug that in, 3 times pi over 6 is pi over 2. The sine of pi over 2 is 1 times 7 is 7. So in the direction of pi over 6, I'm going to go 7 units. There's one of my petals. Now, different students will sometimes make them different width. I'm not going to stress about that. I just want them positioned properly. Well, I want to get more multiples of pi over 2. Like, I don't mind having 3 pi over 2, etc. But I want some more multiples of pi over 2 because those tend to give me where sine has a value of 1 or negative 1. So maybe I'll plug in pi over 2. If I plug in pi over 2, I'd get 3 pi over 2. The sine of 3 pi over 2 is negative 1 times 7 is negative 7. So in the direction of pi over 2, I'm going to go backwards 7 units. So I should have a petal here. I want to get more pi over 2s. I have this multiplier of 3. Why don't I do like another pi over 6, but I'll do 5 pi over 6, because 3 times 5 pi over 6 is really 5 pi over 2, which is the same as pi over 2 again. Right? It's just going around the circle again. Well, if I have a pi over 2 for my argument, sine of pi over 2 is 1 times 7 is 7. 5 pi over 6 is this angle, and I'm going to go out 7 units to draw that petal. But something else that students sometimes notice is that there's 3 petals, and if I divide my circle by 3, every time that I move another 2 pi over 3, I should have another petal. So remember, I'm starting at pi over 6. If I add on 2 pi over 3 to that, 2 pi over 3 is the same as 4 pi over 6. I would land at 5 pi over 6 for my next petal. And if I add 2 pi over 3 again to the 5 pi over 6, remember 2 pi over 3 is the same as 4 pi over 6, I get 10 pi over 6 or 5 pi over, or maybe that's 9 pi over 6. Let's see if adding is hard today, which is the same as 3 pi over 2. Which is where I landed ultimately. I plugged in a pi over 2, but remember I got a negative, so it went backwards. So that could help you also figure out where these petals are, is divide up your circle and move that many units. It's not always easy to do that computation, but it does work. All right, let's think about this one. Oh, and let's also notice I have an odd number of petals on a sine graph. One of my curves is along the y-axis. All right, this one I have 5 cosine of 4 theta. So I should end up on this one with twice as many petals as is listed. I should end up with 8 petals. And these petals, I guess I didn't give us quite enough little circles on this one, but 5 cosine of 4 theta, 8 petals of length 5 each. Well, if I start by plugging in a 0, with cosine I often plug in a 0. 4 times 0 is 0. Cosine of 0 is 1 times 5 is 5. I'm going to, again, just notice that I'm always going to go out 5 units for all of these petals. So along 0, I'll go out 5. 1, 2, 3, 4, 5. Now for this particular graph, I'm taking 2 pi and I'm dividing it up into 8 sections. So every pi over 4, I should have another petal. Well, pi over 4 is like right here. Go another pi over 4, another pi over 4. Remember, pi over 4 is like halfway in between. Some petals are drawn, they're not all equal. I'm sorry. Another pi over 4. Sorry, it's actually quite hard to draw on this screen before you mock me. I think I need to get a new pen. They should not, the petals don't actually overlap. And when you have a lot of them, they start to kind of get thinner so that you have room for all of them. So every time you have a pi over 4, I'll have another one. So I could keep using the table here, but I don't need to. But if I wanted to, I could plug in numbers like pi over 2 would get me 4 times pi over 2 is 2 pi, which is the same as 0. Cosine of 0 is 1 times 5 is 5. So notice I have that there. Now, cosine, you're always going to have at least 1 petal along the x-axis. If it's an even number of petals, you'll have 2 of them. But you have this symmetry. But that's how I would do these rose petals, as I would make a table of values to kind of help me out a little bit. Okay, we have another exploration. This one is also for Mathematic. We're going to go back to the same one. I'm going to close the folders for parts 1 and 2. By the way, the rose curves for most people are the hardest ones. So you made it through that. I'm going to close the folders for parts 1 and 2, open the folder for part 3, and I'm going to look at limacons. Limacons. It's a French word for snails. You might guess that they kind of look like this. They kind of look circular, but have this like kind of indentation a little bit right here. So these end up looking a lot like snails. And we're going to also look at a special type of limacon called a cardioid. Cardioid, you might think of like cartery, heart, etc. In fact, these ones look like a heart. They look like a heart curve as we graph them. Okay, so what we're going to do is turn on equation 10, move the sliders. We won't be using any ends because the angle is not multiplied. That's why we don't have all these petals. And let's just see what happens. And then we're going to sketch each of these. So I'm going to pause this so you can explore a little bit and then sketch these. And then we're going to notice some patterns from there. Just a reminder, turn that one off, close up part 2, and open up part 3, and then start with equation 10. And then explore equation 10, 11, and 12. You can move the sliders around a little bit on these ones and see what happens. Actually, really, equation 10 is the main one. I think equation 10 and 12. You can use both of those.